Hi, everybody. Okay, we're going to take what we just learned about orthogonal sets and extend it to be what we call an orthonormal set. So a set of vectors is called orthonormal if they're all unit vectors and they're an orthogonal set. So the only difference between orthogonal sets and orthonormal sets is that orthonormal sets are all unit vectors. That means then if you take their dot product in that set and the indices are different, well, then their dot product 0. If the indices are the same, then that's actually the length of the vector, which is just 1. An orthonormal basis will just be for some subspace. It's just a basis that's also then an orthonormal set. So an orthonormal basis is just a basis of orthonormal vectors. So I want to convince you then that these two vectors, they form an orthonormal set. They actually are an orthonormal basis for the span of these two vectors, or in this case, the span of the set S. To show that it's an orthonormal set, it's really easy. Just take the dot products first. And notice that that dot product is clearly 0. If you take the length of the vector 1, that length would then be 1 over the square root of 2 squared plus 1 over the square root of 2 with a negative squared. And that's actually a half plus a half, and that's just 1. And then lastly, if you take the length, and that'd be square root of 2 yet, square root yet 2. That's gonna be square root here too. And that's square root. That's of course just 1. So the length of the vector v2 squared would then be the sum of the squares of the components. It'd be 1 over the square root of 6 squared plus 2 over the square root of 6 squared. That'd be plus 1 over the square root of 6 squared. And that is going to be 1 plus 4 plus 1 all over 6. That's 1. So then if the length of the vector squared is 1, then the length of the vector is 1. So these vectors are all unit vectors, and their dot product is 0. So it's an orthonormal set. Easy. Now, what if I gave you, though, an orthogonal set, and from it, you want to form an orthonormal set? Well, they're both already orthogonal. So the only thing you don't have is that you need them to become unit vectors. Remember, if you change the length of a vector, if you change the length of two vectors, you don't actually change the dot product between them. That's because of this bit of algebra. You remember, if you take a scalar times a vector and take its dot product with another vector, that's the same as taking the scalar times the dot product. So if the two vectors are orthogonal already, well, then that dot product is 0, and the scalar multiple of it will still be 0. So you can take any scalar multiple of these vectors in your orthogonal set, and the resulting vectors will still be orthogonal. So all we have to do is make sure that all the vectors are going to have unit length. And we already know how to do that too. All you do is you normalize them. Remember that? You normalize them. So you take each vector and you divide by its length. So if I want to take that orthogonal basis for W and convert it into an orthonormal basis, that would be done like this. So the vector 1, 1, 0, I'm going to just multiply it by 1 over its length. So the length of that vector is the square root of 2. So if you want to write it out and just distribute that, you'd have this vector. You don't have to, by the way, but you can. That's one of the vectors. And then the other vector, I'll take the vector at 1, negative 1, negative 1, and then I'll just divide by its length. So then that would be 1 over the length of that vector is actually square root of 3. And again, if you want, you can just multiply the square root of 3 through, or you can leave it the way it is. I personally like leaving scalars out front, but you don't have to. You know, I would then write this as 1 over the square root of 3. You'd have negative 1 over the square root of 3. You have negative 1 over the square root of 3. So then these two vectors together, this vector, 1 divided by square root of 2, 1 divided by square root of 2, and 0, comma, 1 divided by square root of 3, negative 1 divided by square root of 3, negative 1 divided by square root of 3. These two vectors form an orthonormal set. Is a orthonormal set. And therefore, since they have to have the same span, because all you're doing is changing the lengths of the vectors. So you're not changing the span of the vectors, the span of this set of vectors. So then this is actually an orthonormal basis for W. It's actually an orthonormal basis for W. Nice, right? Really easy. All right, we have one more result. Remember that similar result I gave before? So it's still true because, see, an orthonormal basis is an orthogonal basis So the theorem I gave you before about writing a vector as a linear combination of the vectors in the basis, it's still true. The only added additional thing we get, though, is that we can cut down on the amount of computation. Because when you find the coordinates of the vector W inside a subspace W that has an orthonormal basis, the different coordinates are a dot product of VI with W all over VI dot with VI. But VI dot with VI, that's just the length of the vector I, that's 1, if it's an orthonormal basis. So you can cut out all the divisions. So you get this nice result. Keep in mind, though, that this is still true. The W still is a sum of projections, where you're finding that it's the projection of W upon each of the vectors and the orthonormal basis. So that conceptual idea is still true. It's just that computationally it's a little easier because we don't have to do the dot product of VI with VI because they're all 1 anyway. And I think that's enough for that part of the video.